All right, here we are in section 4.1. We are starting chapter 4, so we're moving right along in our college algebra course. We are going to focus on section 4.1 on exponential functions, which will lead into the next section and the next two after that. So 4.1 to 4.4 kind of tie in together with each other because the two functions that we're really going to work with, the exponential and the logarithmic, are inverses of each other. Just like when we add and subtract, those are inverses. Square and square root, they're inverses. We also, in one of the sections, found inverse functions where we were undoing whole things. So this will tie into that as well. Now, we will keep going with the idea of graphing, but now we look at a different function, and it is the exponential function. And you may hear people say the term, it grows exponentially. Well, this is kind of where we're at. If you're looking at population, it grows exponentially. Decay is exponential growth in a sense. So we want to make sure that we are able to kind of work with those as well. Now, the first thing that your book's going to ask you is to kind of make sure you're able to kind of take numbers to a power in your calculator just so you have that skill going on. We have 3 to the 2.1 power. So some of you may have a caret button. Some of you may have an x to the y button on your calculator. So you want to make sure that you can do these. If you end up having a one-line calculator, you might have to do, I think the same steps are. So if you do 3 and then your caret or your x to the y button, and then a 2.1, you should end up getting what that is equivalent to, which is actually 10.045. I think I've rounded it to the thousandths place. But that should be the answer that you get. Now we can do that with our rational and irrational numbers as the power. So we again would just do 4 caret or x to the y of the square root of 2. So you may have to, if you have a one-line calculator, kind of determine if you're using your phone or something like that, make sure you know how the order. What you should get is 7.103. So you probably want to make sure that you can do that. I'm going to grab my phone because that one might be a little bit tricky on that. Just to see what steps I have to take. So you might have to turn it sideways. So I'm going to, if I'm looking at an iPhone, I have 4 and then I have x to the y is the one that I have. So I'm going to go x to the y, and then you have to get the square root. You have to put 2 square root in first and then hit equal. So here is what I wrote, or here's what I typed. 4x to the y, then I did 2 square root and equals. Those are the steps that you're going to have to take if you're using probably a one-line calculator. The two-line ones obviously are a lot different, okay? Now, if we have this e, now this e is special. We're not going to talk about this. This is what we call the natural exponential, okay? And so there is a button on your calculator. Sometimes it's on the upper part, so you may have to do a second or something like that. On your phone, if you have that, what you have to do is in any one-liner, you have to do 3.3 and then the exponential. E to the x is what it has on your phone. E to the x is what you're looking for on that. And so on the phone, I had to do 3.3 and then type e to the x. If you are one that has a two-line calculator, I know on the calculator, the scientific one that I use, I have to engage that e to the x and then just type in 3.3 and hit equals. I don't believe it has like a little caret. It'll just look like e 3.3. Okay, so make sure that whatever calculator that you use, you end up getting 27.113 as the decimal approximation to that, because our calculators are only as smart as what we enter them in to be. So you want to make sure that you have that going in correctly. Okay, now we're going to look at two basic graphs. One being f of x equaling 3 to the x, and one of them being that natural exponential, that e to the x. And so we're going to look at the graphs of those. The idea of any exponential graph, no matter what base that you have, is the same. It's just that your points are a little bit different, and being able to transform those are going to be the same as well as what we've done before. So we're going to have f of x equaling 3 to the x, and then we're doing f of x equals our e to the x. And remember, that's a natural exponential. Well, if you look at e to the first power, obviously 3 to the first power here is going to be 3, but e is approximately 2.718, and so it is just a number, just like the 3 that we have up here. So don't freak out. I could replace that with 2.718 as the approximate, but that is just an approximate. The exact is that symbol of e, okay? So I'm going to investigate these with a t-chart, and we're going to look at the points -1, 0, 1, and 2, and we're going to plug those in to our function. So I get 3 to the -1 as a negative exponent. Remember, that allows you to flip and make it positive, so we actually get that equivalent to 1/3. If I put 0 in there, 3 to the 0 power, remember that is always equal to 1, no matter what base that you have. If I put 1 in there, 3 to the first equals 3, and when I put 2 in there, 3 squared is equal to 9. So if I graph those 4 points, then at -1, we're at 1/3. At 0, we're at 1, always, for any of these. At 1, we are at 3. And at 2, we are at 9, which is up here somewhere. So what does this look like? It looks similar to kind of our rational functions, but we're actually only going to have one kind of piece of that. If we remember in our last section that there was kind of 2 pieces there. In an exponential, we only have 1. Now, these points right here are our key points when we're working with exponentials. So at 0, we're always at 1. So this point is common for every single exponential, basic exponential that we have. And this is always going to be equivalent to the base. So when you have a power of 1, if your base is 4, it's going to be 1/4. If your base is 2, it's going to be at the point 1/2. So that is an important value to remember when you are shifting things around like what we're going to be here. Now, this does have a horizontal asymptote. Okay? On every exponential, we have a y equaling 0 at a horizontal asymptote. Okay? So y equals 0 is our horizontal asymptote. Now, that is one asymptote that we don't cross. Remember, you can do on horizontals, you can cross them, but for this function, it does not cross at all. Okay? Now, if I do a t-chart with this natural exponential, and then we're going to kind of shift it around down here, as you see, then I'm going to again look at the numbers. -1, 0, 1, and 2. And again, I'm going to plug that into my function. And this is where your calculator comes into play, because we want to go e to the -1. So you want to make sure that you enter that in, and that is equivalent to about 0.368. If I plug 0 in, anything to the 0 power is always 1. If I plug 1 in there, e to the first is approximately 2.718. So again, get away from that notation that it is an e. It is just a number, remember. If I put 2 in there and do e squared in my calculator, then I'm going to get approximately 7.389, okay? So these are the points, not very nice, but they are points that I can plot. At -1, we're at 0.368. At 0, we are always at 1. Don't forget that, 0, 1. At 1, we are at the base, which is approximately 2.78, which is about there. And at 2, we are at the 0.7.36, which would probably be more like up there, okay? So if I graph those points, that is what I have for my natural exponential. So you may want to write that and call it a natural exponential. And we have a horizontal asymptote again here at y equaling 0. That's a horizontal asymptote. We are not going to cross that. Okay, so those are kind of our basics. We're just going to work, I think, in some of your value. Hopefully they do the base of 3. If not, you can always change it with your base of 2. But the idea is still the same when we have our shifts. When I have something grouped with our x, we're going to have a horizontal shift, moving it left or right. If I have something grouped with my x and something plus or minus, that's going to include a vertical shift. If I have a negative here, remember when I had like a negative x squared, it now reflected itself over the x-axis, and here we're going to work with that natural exponential. So remember, on these values, that these two middle pieces are the key values with that, okay? All right, so let's see here. We are looking at this 3 to the x minus 1. I'm grouped with my x, so that is going to be a horizontal shift. And we are going to go to the right by 1. Remember, we always take the opposite of that. Now, there's no vertical shift, so I'm still going to have just this y equaling 0. Now, sometimes I'd like to do this, where if I'm moving over to the right, this kind of represents my new axes. So I'm going to let the blue represent the new axes, but this red means that this is a horizontal asymptote at y equaling 0, okay? This blue axis just kind of gets us set to where the new from the origin, remember that 0, 1 point is going to be very important. And when I have a base of 3, we're going to go over 1 from that new origin and up 3 to get that common point. Now, again, you can plug points in if you want all day long. If I put 0 in here, minus 1, I get 3 to the negative 1, which is a 1/3. So here gives me some good points to get a good sketch on that graph. Okay, but realize this is not a vertical asymptote. This is a horizontal asymptote, but this is not a vertical. Okay, so let's see what happens here. With a shift on, I have a -2, which means we're going to go to the left by 2. And this guy right here means we're going to go down by 1. So if I go left 2, my new axis is here. And down 1, I have a new axis of here. There is always a horizontal axis on here. So this is going to be my horizontal axis at y equals, or not axis, a horizontal asymptote at y equaling 0. And we have a base of 3. So if I remember these points, 0, 1, 1, 3. If I put 2 in and I take it to the third power, I'm going to be at 9. But you don't have to remember, though. Just remember these basic ones, and that should kind of get you that idea of the graph. So here's my new origin. So 0, 1 would be here, according to that new origin. Then over 1 and up 3 would include that nether point that I can then sketch my exponential graph. Okay? When in doubt, always plot points. You do not have to just... Okay, what's going on funky with this board? Alright, so now I have my original exponential. So here's my horizontal asymptote, and I'm going to dot the original exponential. Whoops, at 1, 3, we'd have it 2, 9, and we have it 1/3. So this is my original 3 to the x exponential. Now, remember that with a negative in front, I am doing a reflection over the x-axis. So instead of going 0, 1, if I do a mirror image over this x-axis, I end up getting the point 0, -1. Instead of going over 1 and up 3, I would go over 1 and down 3 to get a new point there. If I go to the left 1 and up 1/3, then we would go to the left 1 and down 1/3. And so if we do 2, 9, obviously we're going to be way down here at 2, -9. So this would actually give me the new graph if I am reflecting over the x-axis. Now, this idea that I did here of this dash, sometimes my students like to see that so that they can see the original and then see it being transformed into whichever direction that it needs to be done. So whichever way that you have or want to do, make sure that you do that. Again, when in doubt, you can always plot points. You can always put in 1, 2, 3, or 0, -1 into that original function and kick out a value. Okay? All right, so this last one here is dealing with our natural exponential. So remember that was a base of 2.718. And so when I have a -4 here on the end of my function, this means we have a vertical shift down by 4 with that negative. So I'm going to have a vertical shift down by 4. So my new horizontal asymptote is here. My new origin basically kind of happens right here at 0, -4. So a main point on any exponential is at 0, 1. So I'm going to go up here. Over 1 and up the base. So over 1 and that base is 2.718. So I'm going to go over 1 and up 1. 2.718 is approximately there. If you remember the other one, -1 was at 0.368 or something like that. So I have that going on. And again, this gives me a nice sketch of what that exponential looks like. Okay. All right, very good. So that's all that we're going to do. We're just going to kind of touch on some of those graphs. But the last piece of this exponential section is dealing with some application. So there's a lot of exponential application in finance when we're mainly working with interest. And so I'm going to give you 2 formulas here on how that they calculate compound interest when you're dealing with a loan or whatever the case may be. Okay, so our investments, whatever. So after T years, the balance A, so the amount that is in our account to end with the principal P, this is the money that we started with, and an annual interest rate of R, which will be a percentage, so like 5%, 8%, 7%. Remember that anytime you work with a percent, you must put it into the decimal form. Like if I have 5%, we have to move our decimal over 2 spots and get 0.05. 7.5% would equal 0.075 when I move my decimal 2 places over. So don't forget to do that. It's given by the following formula. So for the first one, if I compound it over n periods per year, so that means like if I'm compounding it semi-annually, that means that's twice a year. Quarterly would be 4 times a year. Monthly would be 12 times because there's 12 months in a year. 12 times per year. That's what the N represents. Then the amount in our account will be found by taking the principal, how much I put into the account originally, times 1 plus our rate over the number of times it's compounded. And we take that all to the nt power. So multiply n times the number of years that you're going to work on that. Now, the other way that when we compound interest, there is a term called continuously compounding interest. So for continuous compounding interest, the formula of the money in our account is found by taking the principal times our natural exponential to the RT power. So sometimes we refer to this as the PERT formula because we have PERT, but it's P times E to the RT. Remember, this is in an exponential. So they're pretty straightforward. Again, they're just formulas, so as long as you have all the information, all we're doing is plugging in, and you will have to use your calculator to determine these out, okay? So a sum of $10,000 is invested. That's the money that we put in. That in disguise is our P. At an annual rate, here is my R, of 8%, but I have to change it to a decimal. Here's the decimal. I move it 2 places back. The rate that I'm going to use is 0.08. We want to find the balance in the account A after 5 years, so that is our T, subject to quarterly compounding. So we're going to use this one at first. And if I'm looking at quarterly compounding, that is done 4 times a year. So here N is equal to 4. At that point, once I've identified those things, we're going to plug in those values and figure out what our A is. So here's going to be part A. I'm going to use this formula right here, and I'm going to plug in the numbers. P was 10,000, was originally invested. Then I need to take 1 plus my rate, 0.08, divide by the number of times it's compounded per year, which is 4, and then raise that to the 4 in T power, so the 4 times the 5 power, okay? So I'm going to clean this up just a little bit. If you have a one-line calculator, it could be kind of hard. So make sure that you're doing your order of operations in here correctly. First, take 0.08, divide by 4, and add 1. When you do that, you end up, I'm going to rewrite 10,000, you end up with 1.02. 0.08 divided by 4 is 0.02. Add 1 gives me the 1.02 that I'm going to raise to the product of these, which is 20. And that is the part that you want to put into your calculator. So do 1.02, your caret or your x to the y to the 20, hit equals, and times that by 10,000. You should get $14,859.47. So that's how much, if you were to compound it quarterly, would be in your account. You would make almost $5,000 in 5 years. Okay. Part B, what happens if the bank says, well, we're going to do your interest and compound it continuously? So which is the better deal? Okay. So I'm going to use this function now. If I'm continuously compounding it, I'm going to start with my principal, which is 10,000. Then I'm going to multiply that by e to the RT. So I'm going to take 0.08 times 5. Now, you can clean this up just a little bit if you want to do that product of 0.08 times 5. We have our 10,000 times e to the, this is a nope, not 0.04, it's just 0.4. Excuse me. Undo that. Oops, I'll go all the way back. 10,000 times e to the 0.4 power. So again, you want to make sure you can calculate this in your calculator. You'll have to make sure that you just do the e and then do 0.4, or do 0.4 and take it to the e to the x. Times it by 10,000 ends up with an answer. So make sure you get this one, $14,918.25. And so this is comparing the same type of thing, but this is compounding 4 times a year. This is continuously compounding. Which one would you choose as your investment? Which one is better, basically? Which one has the better money? I would choose the compounding it continuously, because you do make a little bit more money in that 5 years. It's only about, what, $70, something like that? No, it's a little bit more than that. No, it's about $70, something like that, 60, $70 more. But if you had a lot invested, it could be a lot more. Okay? All right, very good. So that's all that we're going to hit on with our exponentials. We're going to kind of hit some other things when we talk about logarithmics, but at this point on 4.1 section, all we're looking at is kind of the graphs of those exponentials, being able to transform them around, and as well practice some of these formulas dealing with exponentials. So until next time.